Hello everyone, and welcome back to another study shed video. Today we'll be going over the topic of solving second-order homogeneous differential equations with constant coefficients, this time utilizing the method of solving them with characteristic equations that have imaginary roots. So previously we went over characteristic equations. Let's write the general form: ar squared plus br plus c equals 0, in which r either had, there were two r values, unique r values, or there's only one unique r value. Let's change this to y because they're unique. And all of these numbers were real. Well, today we're going to be going over equations whose characteristic equations have imaginary solutions. So the general form to an imaginary solution is, in this case, r equals a plus bi, where a is the real part and b is the imaginary part. All you need to know about this is that in our general equation, y equals c1 e to the r1, not r1, a 8x, choose x, cosine bx plus c2 e to the ax sine bx, that a and b correspond to the numbers a and b here, correspond to the numbers a and b here, respectively. And so how would we go about solving such a differential equation? Let's do a sample problem. So our sample problem today will be standard second order linear differential equation. Let's start y double prime plus 2y prime plus 5 equals 0. So our characteristic equation is r squared plus 2r plus 5 equals 0, giving us r plus 1. Let's actually show you how it's done. R squared plus 2r plus 1 plus 4 equals 0. R plus 1 squared equals negative 4. R plus 1 equals plus or minus square root of negative 4, which we can rewrite as just the square root of 4 times the square root of I, which is just 2i. So we got plus or minus 2i. Then we just subtract the 1 over to get r equals negative 1 plus or minus 2i. So in the general form, r equals a plus bi. The real part here is this negative 1, and the imaginary part here is 2i. So we know a is equal to negative 1, and b is equal to 2. So plugging that into our general form of a solution to a second order differential equation with complex roots or imaginary roots, we get y equals c1 e to the at cosine bt plus c2 e to the at sine bt. We just replace a with negative 1, or negative 1, and negative 1, and b with 2. And this is our general solution. If we had a initial condition, we could plug it in to solve for c1 and c2. But essentially, that is how you solve such a differential equation. Thank you for watching, and hopefully you learned something new today. And as always, happy studying.